Hello everyone. Today we are diving into an essential concept in computer science, time function and their roles in analyzing the efficiency of algorithms. Understanding how execution time scales with input size is crucial for optimizing our code and ensuring it runs efficiently. Time functions categorize the time complexity of algorithms based on their execution time or resource usage as the input size changes. So, grab your notebook and let's start with a primary class of time functions, focusing first on constant time. The first class we are going to explore is a constant time, which is denoted as big O of 1. In a constant time complexity, the execution remains the same regardless of the size of input. This means whether you are processing one item or a million items, the time taken by the algorithm does not change. Let's look at some simple examples to illustrate this. Suppose we have a function t of n that always returns the value true regardless of the input size. No matter if n equal to 1 or 100 or 10,000, the execution time is always the same, which is 2. Now, consider another function t of n is equal to 8. Again, this function will always take the same time irrespective of how large n gets. It remains 8. We continue with t of n equal to 100, t of n equal to 2000. All these examples represent a constant time complexities because they do not vary with the input size. Accessing an element in array is a classic example of a constant time taking algorithm. This is because you can directly access any element in array using its index without need to traverse the entire list, whether there is 2 items, 3 items or 100 or 1000 items. You can simply access the items using its index. Now, let's move to our next class of time function, logarithmic time, which is denoted as big O of log n. In logarithmic time complexity, the execution time grows logarithmically as the input size increases. This typically occurs in algorithms that reduce the input size by a factor, usually halving it at each step. A prime example of logarithmic time complexity is a binary search algorithm which is applied to a sorted array. In terms of time complexity, a function t of n equal to log n to base 2 or t of n equal to 4 log n to base 6 or t of n equal to log n to base 3 plus 20, all these examples still represent t of n equal to big O of log n because they grow logarithmically as the input size increases, while the constant part remains constant. So here the dominant term is log n. Next, we have sublinear time, which is represented as big O of square root of n. In this time complexity, the execution time grows proportional to the square root of input size. This is less common but applicable in specific scenarios such as certain searching algorithms. Moving on, we have linear time, which is denoted as big O of n. In linear time complexity, the execution time increases directly in proportion to the size of the input. A typical illustration of this is iterating through all elements in a list. Next, we have linearismic time, which is represented as big O of n log n. In this time complexity, the execution time grows in proportion to n times the logarithm of n. This is often seen in efficient sorting algorithms. Next, let's discuss a quadratic time, which is represented as big O of n squared. In a quadratic time, the execution time increases with the square of the input size. This typically occurs in algorithms that involve nested iteration over the data. A classic example is bubble sort. A bubble sort algorithm compares each element with every other element, leading to nested loop structure. Moving on, we have cubic time, which is denoted as big O of n cubed. In cubic time complexity, the execution time grows with the cube of input size. This often occurs in algorithms with 3 nested loops. Both quadratic and cubic time fall under the category of polynomial time, which is often abbreviated as polytime taking algorithms. Polynomial time refers to the complexity that can be expressed as big O of n power k, where k is a constant greater than or equal to 1. This means that the time complexity grows polynomially with respect to the input size. The general formula of polynomial time can be stated as T of n equal to big O of n power k, where T of n is time complexity, n is the size of input n, k is a constant that determines the degree of polynomial. Next, we have exponential time, which is represented as big O of 2 power n. In exponential time complexity, the execution time doubles with each additional input element. This is typical in algorithms that solve problems by exploring all subsets. Finally, let's discuss about a factorial time, which is represented as big O of n factorial. In factorial time complexity, the execution time grows factorially with the size of input. This often seen in algorithms that generate all permutation of a set. Let's summarize the different time complexities we have explored and how they behave with the varying input size. Consider this example. Let's walk through the comparison table step by step, examining how different time complexities behave as we increase the input size. Starting with a constant time. At every value of n, the execution time remains constant. This consistency illustrates the efficiency of a constant time algorithms as they do not depend on the input size. Next, we look to a logarithmic time. At n equal to 1, the value is 0 and it gradually increases to 5 when n reaches 40. This slow growth shows that a logarithmic time remains efficient even for large inputs. Moving on to sublinear time. Here we see the values start at 1 for n equal to 1 and rise to 6.32 when n equal to 40. The growth is moderate, emphasizing that sublinear complexities are effective for moderate-sized data. Now, let's examine a linear time. The execution time directly correlates with n. At n equal to 40, the value is 40, which reflects a straightforward increase. This shows that a linear time algorithm scales directly with the input size. Then we have a quadratic time. Here, we see a dramatic increase. Starting at 1 for n equal to 1, the value jumps to 1600 at n equal to 40. This sharp increase illustrates the inefficiency of quadratic algorithm for larger inputs. Next, we have an exponential time. At n equal to 1, the value is 2, but it skyrockets over a trillion at n equal to 40. This illustrates how quickly exponential time functions become expensive as the input size increases. Finally, let's consider a factorial time. Starting at manageable 1 for n equal to 1, the value balloons to an astronomical value at n equal to 40. This stark increase emphasizes the severe inefficiency of algorithm with a factorial time complexity. As we traverse through the table, it's evident that a constant logarithmic and sublinear time complexities maintain efficiency, even with increased input size. In contrast, a quadratic, cubic, exponential, and factorial time complexities escalate quickly, rendering them impractical for larger datasets. This shows the importance of understanding time complexity when selecting algorithms based on the expected input size. To wrap up our discussion, let's summarize the order of time complexities from the fastest to slowest growth. A constant time is considered as the most efficient time and a factorial time is considered as the expensive time in computational complexity. This hierarchy clearly illustrates how different time complexities scale with increasing input size. Understanding this order is crucial for selecting the right algorithm based on the efficiency and performance needs. Thank you for watching. I appreciate your attention and engagement. If you want an Amharic version of this lecture, leave your comments in the comment section below. Based on the majority voice, I will provide the Amharic version of this lecture. See you in the next video.